What if everything in the universe, from the tiniest particles to the vastest galaxies, follows a hidden blueprint, an invisible order so perfect it shapes reality itself? Picture a snowflake, its delicate arms mirroring each other with impossible precision, or a spiderweb, its threads radiating outward in flawless balance. These glimpses of symmetry in our world might just be echoes of something far grander, a cosmic harmony woven into the fabric of space and time. For centuries, scientists have chased this elusive idea, peeling back the layers of the universe to uncover the secrets of its hidden symmetries. And what they've found will bend your understanding of reality. Symmetry isn't just about beauty or balance, it's the silent architect of the cosmos. It dictates how particles interact, how stars ignite, even how time itself flows. But here's the mind-bending part. Some symmetries are so deeply buried, they only reveal themselves under the most extreme conditions, like in the heart of a black hole or the first moments after the Big Bang. Others might exist in dimensions we can't even perceive, shaping our reality from realms beyond our senses. This isn't just abstract physics, it's a detective story on the grandest scale, where every clue leads us closer to answering the ultimate question: why does the universe work the way it does? Today, we're diving into 30 of the most extraordinary theories that attempt to crack this cosmic code. From the eerie perfection of string theory's vibrating filaments to the twisted symmetries of dark matter, each idea is a piece of the puzzle, a flicker of light in the darkness. Some will sound like science fiction, others might just rewrite the textbooks, but one thing's certain: by the end of this journey, you'll never look at the night sky the same way again. So let's begin where all great mysteries start, with a question. What if symmetry isn't just a feature of the universe, but the very reason it exists at all? Imagine a cosmic dance where every particle in the universe has a hidden twin, a shadowy partner waiting to be discovered. This is the bold promise of supersymmetry, or SUSY, a theory so elegant it could rewrite the rules of reality itself. At its core, SUSY suggests that every particle we know, electrons, quarks, photons, has a mysterious superpartner with slightly different properties. These twins aren't just duplicates, they're cosmic counterparts that could hold the key to unlocking the universe's deepest secrets. Why does this matter? For decades, physicists have struggled to reconcile the messy, fractured nature of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. SUSY offers a breathtaking solution. If these superpartners exist, they could act as cosmic bridges, weaving the forces together into a single, unified framework. It's like finding the missing pieces of a jigsaw puzzle that suddenly make the whole picture click into place. But the implications go even further. One of the most baffling mysteries in modern science is dark matter, the invisible glue holding galaxies together. SUSY superpartners are prime suspects. Some of these elusive particles could be floating through space right now, completely undetectable to our instruments, yet making up most of the matter in the cosmos. It's a tantalizing idea. The very shadows of known particles might be the hidden architects of the universe's structure. The hunt for SUSY is on. Beneath the French-Swiss border, the Large Hadron Collider smashes protons together at nearly the speed of light, searching for traces of these superpartners in the debris. So far, the evidence remains elusive, but the pursuit continues. Because if supersymmetry is real, it wouldn't just solve existing puzzles. It would open doors to realms of physics we've only dreamed of. From extra dimensions to the birth of the cosmos, SUSY fingerprints could be everywhere, waiting to reveal a universe far stranger and more symmetrical than we ever imagined. And here's the mind-bending twist. Even if SUSY isn't proven exactly as predicted, the very search for it has already reshaped our understanding of reality. Sometimes the most profound discoveries aren't about finding what we expect, but stumbling upon something entirely unexpected, hidden in the symmetries we've yet to unravel. Supersymmetry's elegance is undeniable, but elegance alone doesn't make a theory true. For all its mathematical beauty, SUSY faces a glaring hurdle. After decades of searching, we haven't found a single superpartner. The Large Hadron Collider, designed in part to uncover these elusive particles, has come up empty-handed time and again. This absence isn't just disappointing, it's forced physicists to confront an uncomfortable possibility. What if SUSY isn't the answer we thought it was? Critics argue that the theory's flexibility might actually be its downfall. Originally, SUSY predicted superpartners would appear at energy levels well within the LHC's reach. When they didn't, proponents tweaked the models, pushing the predicted masses of these particles higher and higher. To some, this starts to feel like moving the goalposts, adjusting the theory to fit the data rather than letting the data test the theory. It's a bit like a detective insisting a suspect must be guilty, even after alibi checks out. At what point does perseverance become wishful thinking? Yet SUSY isn't down for the count. Some theorists are revisiting its foundations, exploring broken supersymmetry, where superpartners exist but in forms so subtle or short-lived that current experiments can't detect them. Others suggest these particles might hide in extra dimensions, their signatures blurred by realms beyond our perception. There's even a wilder idea. What if superpartners aren't particles at all, but disturbances in the fabric of space-time itself? These adaptations keep SUSY alive, but they also raise a deeper question. How much can a theory change before it becomes something entirely new? The debate reflects a larger tension in physics. Do we cling to elegant ideas because they feel right, or do we let nature have the final say? SUSY endurance speaks to its power, but the universe has a habit of surprising us. Whether supersymmetry survives or falls, its legacy is secure. It's pushed us to think bigger, dig deeper, and question everything we thought we knew about the cosmos. And in science, that's never a waste, even if the truth turns out to be stranger than symmetry. If supersymmetry hints at unseen particles, string theory takes us even further, into realms where the fabric of reality isn't made of points at all, but of unimaginably tiny, vibrating strings. And here's where things get truly bizarre. These strings don't just dance through the 3 dimensions we know, they ripple through 6 or 7 more, hidden from view like folds in cosmic origami. Forget parallel universes, this is about parallel geometries, curled so tightly that a single atom might contain entire landscapes of unseen structure. At the heart of this idea are Calabi-Yau manifolds, exotic, multi-dimensional shapes with such perfect symmetry they could be the universe's hidden blueprints. Picture a snowflake, but instead of 6 arms, it has thousands, twisting through dimensions we can't perceive. These shapes aren't arbitrary. They're mathematical masterpieces where strings vibrate in harmony, their frequencies determining everything from the mass of an electron to the force of gravity. It's as if the laws of physics are musical notes, and Calabi-Yau manifolds are the instruments playing them. But why would nature need extra dimensions? Think of it like this: a telephone wire seen from a distance looks like a simple line, one dimension. Up close, you realize it's a cylinder wrapping around a hidden axis. String theory suggests our universe is like that wire, with dimensions coiled so small they're invisible to us. And just as the wire's hidden curvature affects how signals travel, these compactified dimensions could dictate why particles behave the way they do. The twist: not just any shape will work. Only certain Calabi-Yau configurations produce the symmetries we see in nature, as if the cosmos is a lock and these shapes are the only keys that fit. The implications are staggering. If right, string theory wouldn't just unify physics, it would reveal a universe where every black hole, every star, every quark is a symphony of vibrations in higher dimensional space. Yet for all its elegance, the theory faces a glaring problem. We can't directly observe these dimensions. Some physicists argue they're mathematical fiction. others believe future experiments like gravitational wave detectors might catch whispers of their influence. One thing's certain, if hidden dimensions are real, they'd rewrite not just our textbooks, but our very understanding of existence. After all, what could be more symmetrical than a universe where the tiniest strings and the vastest galaxies are threads in the same multidimensional tapestry? String theory's elegance is undeniable, but beauty alone doesn't make a scientific theory valid. For all its mathematical sophistication, one glaring question lingers: can it ever be tested? Critics like physicist Lee Smolin argue that after half a century, string theory remains trapped in the realm of abstract equations, with no experimental evidence to anchor it in reality. It's a theory that promises everything: unification of quantum mechanics and gravity, hidden dimensions, cosmic symmetry, yet delivers nothing concrete for scientists to observe or measure. Smolin likens it to a grand castle built on sand, breathtaking in design, but with no foundation to prove it's more than an intellectual mirage. Peter Woit, another vocal skeptic, takes the critique further. He sees string theory as a case of "not even wrong," a phrase borrowed from physicist Wolfgang Pauli to describe ideas so vague they can't be falsified. Science thrives on disproof, on experiments that force theories to evolve or collapse. But string theory's flexibility, its ability to morph into countless versions to fit new mathematical insights, makes it nearly immune to failure. It's like playing chess where the rules change every time you're about to lose. Without a way to pin it down, can it ever truly be called physics? Proponents, though, fire back with a compelling counterargument. They point out that Einstein's theory of general relativity seemed untestable at first, too, until an eclipse in 1919 bent starlight exactly as predicted. Some breakthroughs take time, and the tools to probe string theory's claims, like advanced particle colliders or gravitational wave observatories, are only now catching up. The mathematics, they insist, is too elegant, too deeply intertwined with the universe's symmetries to be mere coincidence. It's as if we've found the Rosetta Stone of physics, but haven't yet deciphered the full inscription. The debate cuts to the heart of what science is. Should we chase theories because they're mathematically beautiful, even if they're currently untestable? Or does that risk turning physics into a branch of pure philosophy? For now, string theory remains in limbo, a dazzling idea suspended between inspiration and validation. Whether it ultimately ascends to the status of a theory of everything or fades into obscurity, one thing's certain: it's forced us to rethink the very nature of reality, pushing the boundaries of what we consider possible. And in that sense, it's already changed the game, even if the final answer lies hidden in dimensions we've yet to explore. What if everything you see, the stars, the planets, even your own hands, is nothing more than a cosmic illusion, a shadow cast by information etched onto the fabric of reality itself? This is the audacious claim of the holographic principle, a theory so radical it turns our understanding of the universe inside out. At its core, the idea suggests that the three-dimensional world we experience might just be a projection, a hologram encoded on a distant two-dimensional surface. It sounds like science fiction, but the math behind it comes from some of the sharpest minds in physics, including Nobel laureate Gerard T. Hooft and string theorist Leonard Susskind. The story starts with an unlikely hero: black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, a measure of its hidden information, isn't determined by its volume like you'd expect, but by the area of its event horizon. It's as if all the chaos inside a black hole is somehow written on its surface, like words crammed onto the page of a book. This odd connection between surface area and information planted the seed for something far bigger. What if everything that happens inside a region of space is just a reflection of data stored on its boundary? Enter the holographic principle. Imagine a movie screen. The images appear to have depth, motion, even emotion, but they're really just patterns of light on a flat surface. The holographic universe works the same way. Every particle collision, every supernova explosion, even your thoughts right now could be traced back to bits of information flickering on some distant cosmic horizon. It's symmetry taken to the extreme. The universe's deepest workings might not be about what's inside space, but what's written on its edges. The implications are dizzying. If true, the holographic principle would mean that black holes aren't just celestial vacuum cleaners. They're the universe's ultimate hard drives, storing information in ways we're only beginning to grasp. It could also solve one of physics' biggest headaches, the clash between quantum mechanics and gravity. By treating space-time as an information network rather than a rigid stage, the holographic principle might finally bridge the gap between these warring theories. But here's the real kicker. If our three-dimensional world is just a projection, what or who is doing the projecting? Are we living in some kind of cosmic simulation? Or is this a natural property of how space-time emerges from deeper laws? The holographic principle doesn't answer that yet, but every time a physicist peers into a black hole's abyss or runs the equations on quantum entanglement, they catch glimpses of this hidden symmetry, a universe far stranger and far more interconnected than we ever imagined. And that's the beauty of the idea. It doesn't just reshape reality. It makes you wonder whether we've been looking at dimensions all wrong. Maybe the most profound symmetries aren't in space at all, but woven into the very code that creates it. What if death isn't the end? Not for stars, not for black holes, not even for the universe itself. Roger Penrose's Conformal Cyclic Cosmology dares to suggest that the cosmos doesn't just fade into darkness but reincarnates, cycling through endless iterations like a cosmic phoenix. At the heart of this radical idea lies an astonishing symmetry. The universe's far future might secretly mirror its infancy, with information somehow preserved across the eons. It's a vision so grand it makes the Big Bang seem like just another chapter in an infinite story. Penrose's theory hinges on a peculiar property called conformal symmetry, a kind of geometric harmony that remains intact even as space stretches or shrinks. Picture a chessboard, zoom in or out, and the pattern stays the same. Now imagine that chessboard is the entire universe, its fundamental relationships unchanged even as galaxies dissolve and particles decay. In this view, when our universe reaches heat death, a cold, empty expanse where nothing happens, it doesn't just stop. Instead, it resets, its vast emptiness becoming mathematically indistinguishable from the singularity that birthed the Big Bang. The end becomes the beginning in a loop without end. But how could such a cycle leave traces we might detect? Enter Hawking Point's strange, circular hotspots in the cosmic microwave background, the afterglow of the Big Bang. Penrose argues these could be echoes of supermassive black holes from a previous universe, their evaporating energy imprinting faint rings on the sky. It's as if the cosmos has a memory, fingerprints left by its ancestors. Skeptics counter that these patterns could just be random fluctuations, yet the precision of their alignment keeps physicists intrigued. The implications are dizzying. If conformal symmetry truly bridges cosmic epochs, it would mean the laws of physics aren't just universal, they're eternal. Particles, forces, even consciousness might be part of an infinite tapestry, rewoven in each new cycle. And here's the wildest twist. If information survives these rebirths, could we, or some distant echo of us, exist again in a future universe? Penrose's vision stands at the edge of science and philosophy, challenging not just how we see the cosmos, but our place within it. Whether proven or not, it reminds us that symmetry might be more than a mathematical quirk. It could be the universe's way of whispering its deepest secrets across the void of time. What if the universe's deepest secrets are hidden inside a geometric shape so complex, most mathematicians can barely visualize it? enter the E8 Lie group, a sprawling, 8-dimensional mathematical object with 248 symmetries, where every twist and turn could map onto the fundamental particles and forces of nature. This is the radical vision of physicist Garrett Lissy, whose exceptionally simple theory of everything dares to suggest that the cosmos isn't built from messy equations, but from the pristine symmetries of this extraordinary structure. Lissy's approach is breathtaking in its elegance. Picture the E8 group as a cosmic snowflake, but instead of 6 arms, it has thousands of interconnected facets, each representing a possible state or interaction in particle physics. Electrons, quarks, even the elusive Higgs boson, all might simply be different facets of this single geometric jewel. The theory's boldest claim, gravity, electromagnetism, and the nuclear forces aren't separate phenomena at all, just different perspectives on the same underlying symmetry. It's as if we've been studying shadows on a cave wall, while the true object casting them has been waiting in 8-dimensional space all along. Yet for all its beauty, the E8 theory has glaring holes. The most persistent criticism, gravity. In Lissy's model, gravity emerges naturally from the geometry, but it's far weaker than observed in the real universe. Critics argue this is like building a clock that ticks perfectly, except it loses 3 hours a day. The theory also struggles to explain why particles have the masses they do, or how quantum randomness fits into its rigidly symmetrical framework. Even Lissy admits his idea is incomplete, calling it a work in progress rather than a finished masterpiece. Then there's the mathematical audacity. E8 isn't just complex, it's fiendishly so. Even slicing off a tiny piece for study can take years of computation. Some physicists question whether any theory requiring such abstract machinery can truly describe the messy, probabilistic universe we inhabit. It's like using a sculptor's chisel to perform heart surgery. Precision isn't the issue, but practicality might be. Still, the theory's allure persists. Unlike string theories, hidden dimensions, or supersymmetries, unseen particles, Lissy's model lives entirely within known mathematics, demanding no radical new physics, just a radical reinterpretation of what already exists. And in an era where particle colliders cost billions and experiments grow ever more indirect, the idea of uncovering unity through pure geometry has undeniable appeal. Perhaps the universe isn't a patchwork of theories, but a single, symmetrical truth waiting to be decoded. Whether E8 ultimately succeeds or fails, it reminds us of something profound. The human quest to find order in chaos isn't just about equations. It's about believing the cosmos makes sense, even if that sense is written in dimensions we can't yet see. And sometimes the most revolutionary ideas aren't the ones that answer every question, but the ones that make us ask better ones. Imagine 2 completely different worlds, one a warped, gravity-filled cosmos, the other a flat, quantum realm buzzing with particles secretly describing the same reality. That's the essence of the AD/S/CFT correspondence, a theoretical bridge so profound it's been called the Holographic Principle's mathematical backbone. At its core, this idea suggests that a universe with gravity, like the twisted spacetime of anti-de Sitter space, is perfectly mirrored by a quantum field theory living on its boundary with no gravity at all. It's like discovering that a sprawling, 3-dimensional cathedral is somehow encoded in the brushstrokes of a 2-dimensional painting hanging on its wall. To grasp why this matters, picture a black hole again. Inside, gravity runs wild, warping space and time beyond recognition. But the AD/S/CFT duality implies everything happening inside, every particle swallowed, every law of physics broken, could be translated into a complex dance of quantum information playing out on the black hole's surface. The mind-bending part, these aren't just analogies. The equations governing the quantum painting precisely match those describing the gravitational cathedral, as if the universe is running 2 entirely different simulations of the same event. The implications ripple across physics. For decades, quantum mechanics and general relativity have refused to play nice, one ruling the tiny world of particles, the other governing cosmic scales. But AD/CFT offers a workaround. Maybe quantum fields are gravity, just seen from a different angle. Think of it like ice and water. They seem utterly different, one solid, one liquid, yet both are H2O in different states. Similarly, gravity might just be quantum physics in another phase, with the duality acting as a universal translator, yet the theory isn't perfect. Anti-de Sitter space, with its negative curvature, is a far cry from our own universe's flatter geometry. Critics argue it's like testing a flight simulator that only works in zero gravity, useful for principles but not the real thing. Still, even skeptics admit the correspondence has cracked open problems once deemed unsolvable, from black hole entropy to the nature of spacetime itself. It's as if we've been handed a Rosetta Stone for the cosmos, and we're only beginning to decipher its glyphs. So where does symmetry fit in? The AD/CFT duality reveals a hidden harmony between gravity's chaos and quantum order, suggesting the universe's deepest laws might not be separate at all, just facets of a single, symmetrical truth. Whether this holds for our actual universe remains unknown. But if it does, we might finally understand why reality at its core feels so elegantly interconnected. And that's the real magic of the idea. It doesn't just solve equations. It hints that the universe's greatest secret might be unity itself. Flip the universe like a coin, reverse every particle's charge, run time backward. And according to CPT symmetry, physics should play out exactly the same. This cornerstone principle says the cosmos is fundamentally unchanged if you simultaneously swap charge c, mirror all spatial dimensions p, and reverse the arrow of time t. It's like filming a subatomic reaction, then playing the tape in reverse while flipping the image and turning matter into antimatter. If the footage looks identical, CPT holds. And for decades, every test suggested it did. But then came the kaons, tiny, unstable particles whose bizarre behavior might hold the key to one of the universe's greatest mysteries. Why does anything exist at all? Here's the puzzle. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, leaving behind nothing. Yet here we are, in a cosmos drowning in matter with barely a trace of antimatter. The only way this makes sense is if some process tipped the scales. Enter CPT violation. When physicists studied kaon decays in the 1960s, they noticed something odd. These particles didn't just break down, they did so slightly differently than their antimatter counterparts. It was as if nature had a tiny, built-in preference for matter, a crack in the universe's perfect symmetry. Fast forward to today, and experiments at CERN Antimatter Factory are pushing this frontier further. By comparing the properties of protons and antiprotons with unimaginable precision, scientists are hunting for even the faintest whisper of CPT violation. One experiment, BASE, has already measured antiproton magnetic moments to a precision of 1 part in a billion, and so far the symmetry holds. But the hunt isn't just about confirming or breaking CPT, it's about probing whether the universe's rulebook has hidden loopholes. What makes this so thrilling is the stakes. If CPT isn't absolute, it wouldn't just rewrite textbook. It could explain how a single extra matter particle survived annihilation for every billion pairs in the early universe. That tiny imbalance, amplified over cosmic time, became stars, planets, and us. The kaon's faint asymmetry might seem insignificant, but in a cosmos built on symmetry, even the smallest crack can reshape reality. And that's the beauty of CPT. It's not just a test of nature's balance sheet. It's a search for the reason we're here at all. What if the universe isn't just expanding, but unfolding, repeating its patterns like an infinite cosmic tapestry, where every galaxy cluster mirrors the branching of neurons in your brain, and every atom echoes the spin of distant stars? This is the mesmerizing promise of fractal cosmology, a theory that suggests the cosmos operates with scale symmetry, meaning its structures repeat themselves no matter how far you zoom in or out. It's as if nature has a favorite blueprint, one it uses again and again, from the quantum foam to the vast web of galaxy superclusters. The idea isn't just poetic, it's rooted in observations that defy traditional models. Take the distribution of galaxies, for example. When astronomers map the universe on the largest scales, they don't see randomness or uniform spread. Instead, they find galaxies clumped into filaments and voids, forming a web-like structure that shockingly resembles the branching networks of capillaries in a leaf or the cracks in dried mud. These similarities aren't coincidental. They hint at a deeper, fractal-like organization, where gravity and quantum fluctuations conspire to create order across unimaginable differences in scale. But how could this work? Loop quantum gravity, a leading contender for unifying general relativity with quantum mechanics, offers a clue. In this framework, space-time isn't smooth and continuous but granular, woven from tiny, indivisible loops. These loops interact in ways that could naturally produce fractal geometries like a snowflake growing from simple rules repeated endlessly. If space itself is built this way, it would mean the universe isn't just in a fractal, it is one with every layer of reality reflecting the same underlying patterns. Critics, of course, raise sharp objections. Standard cosmology relies on the cosmological principle, which states that, on large enough scales, the universe is homogeneous and isotropic, essentially the same everywhere. Fractal cosmology turns this on its head. If structures repeat infinitely, there's no true average density of matter, no smooth background. That would force us to rethink everything from dark energy's role to how we measure cosmic expansion. Some physicists dismiss fractal models as mathematical curiosities, arguing that galaxy surveys show homogeneity at the largest scales. Others counter that we simply haven't looked far enough or with the right tools to see the pattern's full extent. Yet the theory's allure persists, partly because it bridges the gap between the cosmic and the quantum. Just as a coastline looks jagged whether viewed from space or a foot above the sand, fractal symmetry suggests the universe's laws might not care about size. A black hole's event horizon and an electron's orbit could be governed by the same geometric principles, just playing out on different stages. It's a radical vision, one where the universe isn't just connected but self-similar, a hall of mirrors reflecting the same beautiful chaos at every turn. The implications are staggering. If the cosmos is fractal, it could mean our observable universe is just one branch of an infinite structure, with other regions following the same rules but at scales we can't perceive. It might also explain anomalies in the cosmic microwave background, those faint temperature variations that some researchers argue align too neatly with fractal predictions. And then there's consciousness. Some theorists, like physicist Carl Bohm, have speculated that the brain's neural networks might resemble the universe's large-scale structure, not by accident, but because both emerge from the same fundamental geometry. Whether fractal cosmology ultimately holds or not, it challenges us to see the universe differently, not as a hierarchy of scales, but as a symphony of repeating motifs. Maybe the cosmos isn't just expanding, maybe it's unfolding, revealing its symmetries one layer at a time. And if so, the greatest discovery awaiting us might not be a new particle or force, but the realization that we've been standing inside the pattern all along. Quantum mechanics is famous for its unpredictability, the unsettling idea that particles don't have definite properties until we measure them, as if reality itself waits for an observer to make up its mind. But what if this randomness is just an illusion, a veil hiding a deeper layer of order? That's the radical proposition of Bohmian mechanics, a theory that dares to rewrite quantum rules with an old-school concept, determinism. At its heart lies the pilot wave, an invisible guide that steers particles along precise paths, like an unseen hand moving chess pieces across a board. The theory traces back to physicist David Bohm in the 1950s, who refused to accept that nature was fundamentally chaotic. Instead, he proposed that every particle has a definite position at all times, riding atop a hidden wave that dictates its motion. Imagine dropping a cork into a flowing river. The cork's path isn't random, it's carried by currents you can't see from the surface. In Bohm's universe, particles behave the same way, with the pilot wave acting as the river's flow, directing everything from electrons to planets with clockwork precision. This isn't just philosophical rebellion. Bohmian mechanics reproduces all the strange predictions of standard quantum theory, wave-particle duality, tunneling, even entanglement, but without the uncertainty. Take the famous double-slit experiment, where particles create an interference pattern as if they're waves. In Bohm's view, each particle passes through one slit, but the pilot wave travels through both, guiding the particle's trajectory in a way that mimics wave behavior. It's a stunningly elegant solution, restoring causality to a realm notorious for its dice rolls. Yet most physicists remain unconvinced, and the reason hinges on a bombshell result called Bell's theorem. In the 1960s, John Bell proved that if hidden variables like Bohm's pilot waves exist, they'd have to be non-local, meaning particles could influence each other instantly, no matter how far apart they are. This spooky action at a distance violates relativity's cosmic speed limit, the speed of light. Standard quantum mechanics embraces this weirdness, treating entanglement as a fundamental feature. But Bohm's theory builds non-locality into its foundation, forcing the entire universe to be interconnected in ways that make even Einstein's ghost uneasy. The debate isn't just academic. Experiments have repeatedly confirmed quantum randomness, with measurements aligning perfectly with probabilistic predictions. Bohmians counter that their theory's determinism is hidden, like the gears of a clock behind its face. Just because we can't see the mechanism doesn't mean it isn't there. But Occam's razor often tips the scales. Why add invisible pilot waves if randomness explains the data just as well? Still, Bohmian mechanics refuses to fade into obscurity. Recent simulations show pilot waves can model quantum systems with startling accuracy, and some researchers argue the theory's intuitive framework could revolutionize quantum computing. It's a reminder that science thrives on dissent, that the most profound breakthroughs often come from questioning what everyone else takes for granted. Whether Bohm was right or not, his legacy endures, a stubborn insistence that beneath quantum chaos there might still be a symphony, and in that symphony every note has its place. Why do the fundamental constants of nature, the speed of light, the strength of gravity, the mass of an electron, seem perfectly balanced to allow life to exist? Tweak any one of them just slightly, and stars wouldn't ignite, atoms would never form, and the universe would be a vast, lifeless void. This uncanny precision is what physicists call fine-tuning, and it's led to one of the most provocative ideas in modern cosmology, the anthropic principle. At its core, this principle suggests that the universe's symmetries and constants aren't arbitrary, they're necessary for observers like us to exist. But does this mean the cosmos was somehow designed for life, or is there a stranger, more statistical explanation? The numbers are staggering. Take the cosmological constant, which governs the acceleration of the universe's expansion. If this value were even a fraction larger, galaxies would have been ripped apart before life could evolve. If it was smaller, the cosmos would have collapsed back on itself eons ago. Similarly, the strong nuclear force, the glue holding atomic nuclei together, is calibrated to within 1% of perfection. Any stronger, and hydrogen would fuse too rapidly, burning out stars before planets could form. Any weaker, and no elements heavier than hydrogen would exist. These aren't just happy accidents, they're razor-thin margins that seem to defy randomness. Proponents of the strong anthropic principle argue these coincidences point to something deeper, perhaps even intentionality. Philosopher John Leslie likens it to a firing squad of 100 marksmen all missing their target. The odds aren't just low, they're suspicious. Could some form of cosmic fine-tuner have set the dials? Others, like physicist Freeman Dyson, take a more poetic view, suggesting the universe knew we were coming, with its laws acting as an invitation for life. But there's a competing, less mystical explanation, the multiverse. If our universe is just one of countless bubbles in an infinite cosmic foam, each with randomly dialed constants, then it's no surprise we find ourselves in the rare one where conditions permit existence. In this view, fine-tuning isn't a puzzle to solve but a selection effect. We couldn't observe a universe that wasn't life-friendly because in those barren worlds there'd be no one to notice. String theory's landscape of possible universes lends credence to this idea, with some estimates suggesting 10 to the power of 500 potential vacuum states, each with different physical laws. Critics, though, dismiss the anthropic principle as a cop-out, a way to avoid harder questions. Nobel laureate Steven Weinberg once grumbled that it's a term used for the resignation of physicists. If every observation can be explained by saying, well, otherwise we wouldn't be here, does the principle actually predict anything? Worse, it risks veering into untestable metaphysics. How do you falsify the idea of a multiverse when, by definition, other universes would be forever beyond our reach? Yet the debate isn't just academic. The anthropic principle forces us to confront the very nature of scientific explanation. Is our universe's harmony evidence of deeper laws waiting to be uncovered, or are we reading meaning into what's essentially a cosmic lottery ticket? Perhaps the answer lies somewhere in between. Some theorists now explore weak anthropic reasoning, not as a claim about design or multiple universes, but as a tool to guide which questions are worth asking. After all, if a theory predicts a universe inhospitable to life, maybe it's the theory that needs revising, not the cosmos. What's clear is that fine-tuning touches something primal in us, a longing to know whether the universe is purposeful or profoundly indifferent. Whether you see it as science's most profound clue or its most frustrating dead end, one thing's certain: the mere fact that we're here to ponder these questions is itself a symmetry worth marveling at. And that might be the most haunting truth of all. What if every time you looked in a mirror, the reflection wasn't just an illusion, but a doorway to an entire parallel universe? This isn't the plot of a sci-fi novel. It's the startling premise of mirror matter theory, a bold idea suggesting that nature's symmetry runs so deep, it's woven an invisible twin to our own reality. At the heart of this concept lies parity symmetry, the principle that the laws of physics shouldn't care whether you're watching a reaction unfold normally or through a mirror. Flip an experiment left to right and everything should play out identically. But in the 1950s, physicists were stunned to discover that this symmetry breaks down in certain radioactive decays. The universe, it seemed, had a secret-handedness. Mirror matter theory offers a jaw-dropping solution. Maybe parity is perfectly preserved, but only if we account for an entire shadow cosmos where left and right are flipped. Imagine a world where your reflection isn't just reversed, it's made of entirely different particles, interacting through their own version of the forces we know. Electrons, quarks, even photons would have mirror counterparts, identical in mass but deaf to our light and gravity. These particles wouldn't just be theoretical curiosities, they could solve one of astronomy's biggest mysteries. When astronomers measure galaxy rotations or study the bending of light around galaxy clusters, they find far more gravitational pull than visible matter can explain. If mirror particles exist, their combined mass would perfectly account for this missing influence without needing exotic dark matter candidates like WIMP or actions. It's an elegant 2-for-1, restore nature's symmetry and explain the invisible scaffolding of the cosmos. But how could such a mirror universe hide from us? The answer lies in a concept called kinetic mixing, a faint interaction between ordinary and mirror particles. Think of it like two tuning forks vibrating at nearly the same frequency, close enough to whisper to each other but too far apart to resonate fully. This weak coupling could let mirror matter briefly leak into our world, leaving behind subtle traces. Some physicists speculate that certain neutron stars might accumulate mirror matter cores, altering their cooling rates in detectable ways. Others hunt for mirror particles in high-energy collider experiments, where a fraction of missing energy could signal a particle slipping into the shadow realm. Critics, of course, raise eyebrows. If mirror matter is everywhere, why haven't we seen direct proof? The theory's defenders counter that we might already have just misinterpreted the clues. Take the notorious "oh my god" particle, an ultra-high-energy cosmic ray that seemingly defies known physics. Could it be a mirror proton, accelerated by mirror magnetic fields and crossing over through a rare interaction? Even more provocative is the idea that mirror matter could form its own stars, planets, even life, completely undetectable except through gravity's faint tug. The implications spiral outward. If mirror matter is real, it wouldn't just fill the dark matter gap, it would redefine our place in the cosmos. We might be living in one half of a grand duality, forever separated from our mirror siblings by an insurmountable yet deeply symmetrical divide. And that's the real beauty of the idea. It challenges us to see the universe not as a solo act, but as a cosmic duet with every particle, every force singing in perfect mirrored harmony. Whether the theory holds or collapses, it reminds us that nature's symmetries might be more profound and more hidden than we ever dared to dream. What if space-time isn't the foundation of reality, but a secondary effect, a shimmering mirage emerging from something far stranger? Roger Penrose's twister theory flips conventional physics on its head, proposing that the universe's true building blocks aren't points or strings, but elusive geometric entities called twisters. Picture them as cosmic threads weaving through a higher dimensional space, encoding both position and momentum in a single, elegant twist. Unlike string theory's labyrinth of extra dimensions, twisters thrive in a realm where space-time itself is derived, not assumed. It's as if we've been studying shadows cast by a spinning top, while Penrose invites us to reach out and grasp the top itself. At its core, twister theory is a radical reimagining of geometry's role in physics. Traditional approaches treat space-time as a stage where particles perform, but Penrose suggests the stage is an illusion. The real action happens in twister space, where light rays and particle trajectories are fundamental, not the points they pass through. Think of it like tracing a song's melody on sheet music rather than plotting each note's position in a concert hall. This shift isn't just philosophical, it simplifies notoriously thorny quantum gravity calculations. Problems that choke supercomputers in conventional frameworks sometimes dissolve into elegant algebra when viewed through the twister lens, one of the theory's brightest sparks. Its ability to tame infinity. In general relativity, black holes harbor singularities, points where curvature and density explode to infinite values and equations break down. Twister mathematics smooths these jagged edges, offering finite descriptions where standard physics sees only chaos. It's akin to replacing a shattered mirror with a polished lens, revealing clarity where once there was only fracture. This has profound implications for unifying quantum mechanics and gravity, two frameworks that traditionally clash over how to handle extreme conditions. Yet twister theory isn't without skeptics. For all its mathematical beauty, it struggles to incorporate matter particles as seamlessly as it does light and gravity. While strings vibrate in ways that naturally give rise to quarks and electrons, twisters excel at describing massless entities like photons. Reconciling this gap is like crafting a symphony where only the woodwinds know the score, the brass and strings are still tuning up. Some physicists argue this limitation relegates twisters to a niche role, a toolbox for specific problems rather than a theory of everything. But Penrose's vision is far from stagnant. Recent advances like amplitude-hadron geometry in particle physics borrow twister-inspired tricks to sidestep mountains of calculation, yielding results with jaw-dropping efficiency. And in the quest to quantize gravity, twisters offer a path less traveled, one where space-time's fabric isn't stitched from tiny loops or strings, but spun from deeper symmetries waiting to be decoded. Whether twister theory ultimately unseats string theory or not, its legacy is secure. It reminds us that sometimes the most revolutionary ideas come not from adding layers to reality, but from peeling them back. After all, if space-time is indeed a secondary effect, what other illusions might we be taking for granted? The answer could rewrite physics, not by building a bigger theory, but by revealing a simpler one hidden in plain sight. In the 1930s, physicist Paul Dirac stumbled upon a peculiar numerical coincidence so striking it seemed to whisper of hidden cosmic harmonies. He noticed that the ratio of the universe's age to the time it takes light to cross an atom, a staggering number around 10 to the power of 40, mirrored the ratio of the electric force holding atoms together to gravity's feeble pull. This wasn't just a random alignment. Dirac suspected it revealed a profound symmetry woven into the fabric of reality itself. His large number hypothesis proposed an audacious idea. These ratios aren't accidental constants but evolving relationships, with gravity weakening over cosmic time to preserve their balance. Imagine a universe where the fundamental forces aren't fixed but dance in lockstep, scaling together like gears in a cosmic clock. Dirac's intuition rattled the foundations of physics because it challenged one of science's deepest assumptions, that nature's constants are truly constant. If he was right, the strength of gravity today might differ from its value billions of years ago, subtly altering the universe's expansion rate and even the lifetimes of stars. This wasn't idle speculation, it had testable consequences. For instance, a varying gravitational constant would leave fingerprints in the ancient light of quasars or the precise orbits of distant pulsars. Early searches came up empty, but Dirac's hypothesis refused to die. Instead, it morphed into something even more intriguing. Modern cosmologists have resurrected the spirit of Dirac's idea through theories like scalar tensor gravity, where the strength of gravity fluctuates in tandem with an invisible field permeating space. Some versions of string theory also flirt with varying constants, suggesting that what we perceive as fixed laws might be local equilibria in a much vaster landscape of possibilities. The most tantalizing twist, Dirac's ratios could be clues to a deeper principle, perhaps a holographic one, where the universe's large-scale structure emerges from microscopic rules encoded on its boundary. It's as if the cosmos is solving an equation where the constants aren't inputs but outputs, dynamically adjusting to preserve a hidden symmetry. Critics, of course, remain skeptical. Precision measurements of atomic clocks and lunar laser ranging show gravity's strength hasn't budged more than 1 part in a trillion over the last decade. Yet defenders counter that Dirac's vision might operate on timescales too vast for current tools to catch, like trying to measure a glacier's movement by watching it for a second. Others argue the large numbers aren't coincidences but inevitable consequences of observer selection. In any universe complex enough to harbor life, such ratios would have to fall within a narrow range, or we wouldn't be here to notice them. What makes Dirac's hypothesis endure isn't just its boldness, but its poetic resonance. In a cosmos where galaxies spin and particles collide, his numbers whisper of a grander pattern, a symmetry so vast it spans from the quantum realm to the cosmic horizon. Whether proven or not, the idea reminds us that the universe might not just have laws, it might be a law, unfolding in rhythms we're only beginning to hear. And sometimes the most revolutionary insights begin not with equations, but with a quiet question. What if the constants aren't constants at all? Why does matter exist at all? If the Big Bang created equal parts matter and antimatter, they should have annihilated each other in a blaze of pure energy, leaving nothing behind but radiation. Yet here we are, surrounded by galaxies, planets, and atoms, clear evidence that somehow, someway, the universe tipped the scales. This cosmic imbalance, known as baryon asymmetry, is one of physics' most profound puzzles. And the answer might lie in three radical conditions proposed by Soviet physicist Andrei Sakharov, rules that explain how symmetry had to shatter for our existence to even be possible. Sakharov's first condition sounds simple. The universe must have processes that don't conserve baryon number. Baryons, particles like protons and neutrons, were long thought to be indestructible in their totality. But Sakharov realized that if certain reactions could create slightly more baryons than antibaryons, even by a billionth of a percent, that tiny surplus might survive annihilation. The second condition demands something even stranger: violations of both charge symmetry C and charge parity symmetry CP. Normally, physics treats matter and antimatter as mirror images, but Sakharov showed that if these symmetries fail, if antimatter doesn't quite mirror matter's behavior, it could bias the universe toward matter's survival. The final piece is cosmic non-equilibrium. In the searing heat of the early universe, particles and antiparticles were constantly colliding and recreating each other. For asymmetry to stick, Sakharov argued, this equilibrium had to be disrupted, perhaps by the universe's rapid expansion during inflation, freezing the imbalance into place before annihilation could wipe it clean. Together, these conditions sketch a recipe for how a perfectly symmetrical cosmos could fracture into the lopsided reality we know. But where do we see these rules in action? Neutrinos might hold the key. These ghostly particles barely interact with matter, but they're central to a process called leptogenesis. Imagine heavy neutrinos decaying in the early universe. If these decays violate CP symmetry, producing slightly more matter than antimatter, they could generate an initial excess of leptons, electrons, and their cousins. Through intricate particle interactions, this lepton asymmetry might then convert into the baryon asymmetry we observe today. It's like a cosmic Rube Goldberg machine, where neutrinos tip the first domino in a chain that ends with stars, planets, and us. The smoking gun could be right under our noses. Experiments like Japan's T2K and the Deep Underground Neutrino Experiment in the US are hunting for CP violation in neutrinos. If they find it, it wouldn't just solve the matter-antimatter riddle, it would prove that the universe is fundamentally, beautifully imperfect, because sometimes the most important symmetries aren't the ones that hold, but the ones that break. And in that breaking, the cosmos found room for everything we know. Imagine hurtling through space in a rocket, constantly accelerating, when suddenly your sensors pick up a faint glow of heat, particles flickering into existence all around you. Yet to someone floating motionless nearby, the void remains utterly empty. This bizarre phenomenon is the Unruh effect, a mind-warping prediction of quantum field theory where motion itself conjures particles from nothingness. It's as if the universe keeps two sets of books, one for observers at rest, another for those in motion, with each perspective revealing a different layer of reality's hidden symmetries. At its core, the Unruh effect hinges on a radical idea. What we call empty space isn't truly empty. Quantum fields permeate every corner of the cosmos, seething with virtual particles that flicker in and out of existence too quickly to detect. For an inertial observer, these fluctuations average out to zero, but accelerate and something extraordinary happens. The act of acceleration distorts the observer's perception of time and space, stretching quantum fluctuations until they freeze into real, detectable particles. The faster you accelerate, the hotter this phantom glow becomes, following an exact thermal formula that mirrors the radiation emitted by black holes. It's nature's way of whispering that acceleration and gravity, two seemingly distinct forces, might be sides of the same coin. the connection to black holes is where things get truly profound. In the 1970s, Stephen Hawking stunned the physics world by showing that black holes aren't the perfect traps we once thought. They slowly leak thermal radiation, Hawking radiation, due to quantum effects near their event horizons. Strikingly, the math governing this radiation is nearly identical to the Unruh effect's equations. An observer falling into a black hole would see empty space, while someone hovering outside would witness a fiery glow. This parallel isn't coincidence. It hints at a deep symmetry between acceleration and gravity, suggesting that thermodynamics and quantum mechanics are entangled in ways we're only beginning to grasp. Critics initially dismissed the Unruh effect as a mathematical quirk, since the accelerations needed to produce detectable radiation are mind-bogglingly extreme, far beyond anything our technology can achieve. But recent experiments with ultra-sensitive quantum systems like superconducting circuits have begun teasing out analogous effects in the lab. By simulating extreme acceleration in controlled settings, physicists are testing whether these quantum symmetries hold and whether black holes really are the cosmic accelerators the math suggests. What makes the Unruh effect so revolutionary isn't just its weirdness, but its implication that reality is profoundly observer-dependent. The particles you see depend on how you're moving, blurring the line between what's real and what's a quirk of perspective. It's a reminder that the universe's symmetries aren't just out there, they're woven into the very act of observation itself. And if accelerating through empty space can summon particles from the void, what other illusions might our stillness be hiding? Black holes are cosmic enigmas that appear to erase information from the universe, a direct affront to one of quantum mechanics' most sacred principles, unitarity, the idea that information can never be truly lost. When Stephen Hawking revealed that black holes slowly evaporate through radiation, it sparked a crisis in physics. If a black hole vanishes entirely, what happens to all the information it swallowed? Does it simply disappear, violating the symmetry that governs quantum evolution, or is it somehow preserved in the radiation's faint whisper? This is the black hole information paradox, a puzzle so profound it threatens to upend our understanding of reality's deepest symmetries. Hawking's original argument was grimly elegant. As a black hole emits radiation, it loses mass, shrinking until it vanishes entirely. But the radiation seemed random, carrying no trace of the particles that fell in. It's like burning a library and claiming the smoke somehow encodes every book's contents, except no one could find the cipher. For decades, physicists wrestled with this paradox, torn between Hawking's math and their intuition that information must be conserved. The stakes couldn't be higher. If unitarity fails at black holes, it might fail everywhere, undermining the foundation of quantum theory itself. Enter the firewall proposal, a radical solution that borders on the surreal. Imagine falling toward a black hole's event horizon, expecting the smooth spacetime predicted by general relativity, only to hit a searing wall of high-energy particles just before crossing. This firewall would obliterate you, but in doing so, it might scramble your quantum information into the outgoing radiation. It's a violent fix, stitching information preservation into the laws of physics at the cost of Einstein's graceful spacetime continuum. Critics argue firewalls are overkill, patching one paradox by creating another. If they exist, why don't we see their telltale flashes in the cosmos? A more elegant alternative lies in soft hair, a concept that gives black holes a subtle quantum frizz. Theorists like Andrew Strominger suggest that when particles fall into a black hole, they leave behind faint imprints, low-energy photons or gravitons on its horizon. These soft hairs could encode information like grooves on a vinyl record, preserving it even as the black hole evaporates. The idea hinges on symmetries deeper than we once imagined, linking gravitational physics to quantum field theory in unexpected ways. Yet the debate rages on. Some argue that resolving the paradox requires rewriting quantum mechanics entirely, while others believe we're missing a hidden symmetry that bridges the gap. Recent breakthroughs in holography and string theory suggest information might escape via entangled particles, a quantum sleight of hand where the answer was hiding in plain sight all along. The paradox isn't just academic. It forces us to confront whether the universe plays by neat, symmetrical rules or if reality is messier than we thought. Every proposed solution, firewalls, soft hair, or something stranger, pushes us closer to a theory that marries gravity and quantum mechanics. And in that marriage, we might finally learn whether information, like energy, is truly eternal, or if black holes are the universe's ultimate shredders, defying symmetry for the sake of cosmic mystery. For centuries, scientists have clung to the cosmological principle, the comforting idea that on the largest scales, the universe is homogeneous and isotropic, smooth and uniform no matter where you look. But what if this cornerstone of modern cosmology is wrong? Cracks in this assumption first appeared with the discovery of the axis of evil, a bizarre alignment in the cosmic microwave background radiation that defies randomness. This pattern, stretching across billions of light years, suggests the universe might have a preferred direction, like a cosmic fingerprint smudged across the sky. The implications are staggering. If the axis of evil is real, not just a statistical fluke, it would mean the Big Bang wasn't perfectly symmetrical, and the universe's expansion wasn't the same everywhere. Some regions might have stretched faster, others slower, leaving behind faint but detectable ripples in space-time. This would rewrite one of cosmology's most sacred rules, that no place in the universe is special. Suddenly, we'd have to grapple with the possibility that our cosmic neighborhood isn't a random speck, but part of a grander, asymmetrical structure we don't yet understand. Enter the Bianchi models, a family of cosmological solutions that ditch the isotropic assumption. These frameworks allow for universes that rotate or shear as they expand, creating preferred directions that could explain the CMB anomalies. Picture a balloon inflating unevenly, some parts stretching more than others rather than the smooth, symmetrical expansion we've long assumed. Some versions of these models even incorporate dark energy in ways that fit observational data better than the standard cosmology. Yet the debate is far from settled. Skeptics argue the axis of evil could be an illusion, a trick of incomplete data or foreground interference from our own galaxy. Others propose less radical fixes, like tweaking inflation theory to allow for slight asymmetries without abandoning homogeneity entirely. But the very existence of this debate reveals something profound. Our cosmic maps might be missing entire continents of structure hidden in plain sight. What's at stake isn't just a technical detail, it's the foundation of how we interpret everything from galaxy distributions to the fate of the cosmos. If the cosmological principle falters, we might need to rethink not just where we are, but what the universe fundamentally is. And that's the beauty of science at its best. Even our most cherished assumptions must bend when nature whispers otherwise. What if the smooth, continuous space-time we take for granted is actually an illusion, a fuzzy, jittery canvas where coordinates don't neatly line up like grid points on a map? Elaine Kahn's non-commutative geometry proposes exactly this, a universe where positions and directions refuse to follow the rigid rules of classical geometry, creating a hidden symmetry far stranger than anything Euclid imagined. At its heart lies a simple but profound mathematical twist, the idea that measuring position in one direction might depend on the order you measure it in, like trying to read a book where the words rearrange themselves based on which page you turn to first. This isn't just abstract math. Non-commutative geometry could unify two seemingly unrelated worlds, the bizarre quantum realm and the vast cosmic stage of general relativity. In ordinary geometry, distances commute, measuring a room's length and width gives the same result no matter which you check first. But at the Planck scale, where quantum foam churns, Kahn suggests space-time might behave more like matrices in quantum mechanics, where a times b doesn't equal b times a. This subtle non-commutativity could explain why particles have the properties they do, weaving the standard model's tangled web of forces and particles into a single geometric tapestry. Take the Higgs boson, for instance. In Kahn's framework, this elusive particle isn't just another quantum fluke. It emerges naturally as a kind of geometric vibration, a ripple in the non-commutative fabric of space itself. Even more strikingly, the theory predicts the Higgs mass with surprising accuracy, a feat traditional approaches struggle with. It's as if the universe's most puzzling particle has been hiding in plain sight, disguised as a glitch in geometry's usual rules. Critics raise eyebrows at the theory's abstract machinery, questioning whether such mathematical elegance truly mirrors nature's chaos. Yet experiments at the Large Hadron Collider have begun probing these ideas indirectly, hunting for faint traces of non-commutativity in high-energy particle collisions. Some models suggest that if space-time is fuzzy at tiny scales, it could subtly alter how particles scatter, leaving fingerprints in the debris. What makes non-commutative geometry so compelling isn't just its potential to tidy up physics' loose ends. It's the way it reframes our very notion of symmetry. Instead of perfect shapes and rigid transformations, symmetry here becomes a dynamic, almost musical interplay between order and ambiguity, where the universe's deepest harmonies might be written in a language we're only beginning to decode. And if Kahn's is right, the next revolution in physics won't come from discovering new particles or forces, but from realizing that the stage they dance on was never what we thought it was. What if every time two particles become entangled, a microscopic wormhole silently stitches them together across the void of space? This is the radical proposal of the ER equals EPR conjecture, a theory so audacious it dares to unite the two most stubbornly incompatible frameworks in physics: quantum mechanics and general relativity. The idea traces back to a pair of landmark papers published just months apart in 1935. One, by Einstein and Rosen, described hypothetical bridges in spacetime now called Einstein-Rosen wormholes. The other, by Einstein, Podolsky, and Rosen, highlighted the bizarre phenomenon of quantum entanglement, where particles separated by vast distances share instantaneous correlations. For decades, these concepts lived in separate realms until physicist Juan Maldacena and Leonard Susskind spotted something extraordinary. The mathematics describing them were eerily similar, as if nature had been leaving breadcrumbs all along. Think of entanglement like a cosmic phone call. When two particles become entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Conventional physics treats this as spooky action at a distance, but ER equals EPR offers a tangible mechanism. What if these particles aren't communicating faster than light, but are secretly tethered by Planck-scale wormholes, tunnels so tiny they'd make a proton look gigantic? In this view, entanglement isn't magic, it's geometry, with space-time itself folding to connect what appears distant. Picture two friends whispering through a paper-cup telephone. The string between them isn't just a metaphor, but the fabric of reality warping to preserve a deeper symmetry. The implications ripple across physics. Wormholes, long considered unstable curiosities requiring exotic matter, might be ubiquitous in the quantum realm, woven into the universe's fabric like threads in a tapestry. This could explain why black holes, those masters of spacetime warping, also seem to obey entanglement's rules, a connection highlighted by the firewall paradox. If ER equals EPR holds, the event horizon of a black hole might be studded with wormholes leading to its entangled Hawking radiation, preserving information without fiery paradoxes. It's as if the universe keeps its books balanced not with brute force but with hidden shortcuts, yet skeptics raise valid concerns. If wormholes underpin entanglement, why don't they transfer physical objects or information faster than light? The theory's proponents argue these wormholes are non-traversable, more like abstract tunnels in the equations than gates you could stroll through. Others question whether the conjecture is truly testable. Can we distinguish spacetime stitching from plain old quantum weirdness? Some hopeful signs come from holography, where simulations of entangled quantum systems produce geometries resembling wormholes, suggesting the math might be onto something profound. What makes ER equals EPR so electrifying isn't just its potential to reconcile gravity and quantum mechanics, but the way it reframes our cosmic perspective. Entanglement, once seen as a ghostly abstraction, could be the fingerprint of spacetime's hidden architecture, a reminder that the universe's most profound symmetries might not live in the laws we see, but in the invisible threads weaving them together. And if that's true, then every entangled pair, from lab experiments to particles forged in the Big Bang, might be whispering the same secret. The geometry of connection is written into the universe's blueprint. Picture a geometric shape so powerful it can calculate the outcomes of particle collisions without ever mentioning space or time, a mathematical jewel where the messy complexity of quantum fields collapses into pure symmetry. This is the amplituhedron, a discovery so revolutionary it makes even seasoned physicists pause. Born from the work of Nima Arkani-Hamed and Jaroslav Tiarenkaye in 2013, this multi-dimensional structure sidesteps the traditional framework of Feynman diagrams, those tangled webs of virtual particles physicists have relied on since the 1940s, and replaces them with an elegant geometric dance. At its core, the amplituhedron embodies a radical shift in perspective. Normally, predicting how particles scatter after a high-energy collision requires tracking countless possible paths, each with their own probability amplitudes. It's like mapping every possible detour a traveler might take between two cities, an exhausting, inefficient process. The amplituhedron strips this down to its essential geometry. Instead of summing infinite probabilities, you simply carve out the volume of this shape, and its internal symmetries spit out the correct answer. It's as if the universe has been hiding a shortcut all along, a cosmic cheat code written in the language of polygons and facets. What makes this breakthrough earth-shaking is its implications for spacetime itself. The amplituhedron's calculations work without referencing locality or unitarity, two pillars of conventional physics. Locality, the idea that particles interact at specific points in space, and unitarity, the rule that probabilities must sum to one, seem almost sacrosanct. Yet here's a tool that ignores both and still gets flawless results. This suggests spacetime might not be fundamental but emergent, a secondary effect of deeper geometric symmetries we're only beginning to uncover. The amplituhedron's elegance shines brightest in Yang-Mills theory, the mathematical backbone of the Standard Model. Traditionally, calculating scattering amplitudes here required heroic effort, with pages of algebra yielding meager results. But with the amplituhedron, certain computations that once took weeks now fit on a napkin. It's like swapping a labyrinth for a straight line, with the geometry itself ensuring every step is inevitable, every outcome preordained by its symmetrical perfection. Yet for all its beauty, the amplituhedron isn't a panacea, at least not yet. It currently applies best to highly supersymmetric theories, idealized versions of reality where particles have perfect mirror partners. Our universe, with its broken symmetries and messy quantum fluctuations, resists such neat packaging. Critics argue this limits the shape's practical reach for now. But proponents counter that the amplituhedron's true value lies in its hint of a deeper truth, that the universe's laws might ultimately be geometric, not algebraic. Imagine a future where physicists navigate particle physics not with chalkboards of equations, but by manipulating shapes in higher dimensional space. The amplituhedron offers a glimpse of that world, one where the universe's hidden symmetries aren't just described by math, but are the math etched into the very geometry of existence. And if that's true, then the most profound discoveries awaiting us might not be new particles or forces, but new ways of seeing the patterns that have been there all along. Black holes and neutron stars seem as different as cosmic objects can get: one a crushing void where even light can't escape, the other a blazing, hyper-dense remnant of a dead star. But what if these extremes are just two faces of the same cosmic coin? A daring new theory suggests these objects might be connected by a hidden symmetry, transforming from one state to another like water freezing into ice or vaporizing into steam. The key lies in the eerie similarities lurking beneath their surface differences. Take their formation. Both black holes and neutron stars are born from the catastrophic collapse of massive stars, their destinies decided by fractions of solar mass. A star that leaves behind a core slightly too heavy becomes a black hole. One just under the threshold becomes a neutron star. This razor's edge balance hints that the two might exist on a spectrum, not as separate categories. Now, gravitational wave detectors like LIGO and Virgo are uncovering even more tantalizing clues. When these instruments captured the collision of a black hole with a neutron star in 2019, they recorded vibrations that didn't quite match expectations. The neutron star's behavior in its final moments resembled matter teetering on the brink of collapse, as if it were moments away from shedding its identity and crossing the threshold into a black hole itself. This duality isn't just about mass. Quantum effects deep within neutron stars might be pulling the strings. Under unimaginable pressure, the neutrons in these stars could dissolve into a soup of quarks and gluons, a state known as quark matter. Some models suggest this exotic phase could act as a hidden intermediary, a cosmic stepping stone between neutron stars and black holes. Picture a neutron star so compressed that its internal quarks rearrange into a configuration indistinguishable from a black hole's event horizon, not by collapsing infinitely, but by undergoing a phase transition like water becoming ice at a critical temperature. The implications rewrite astrophysics. If neutron stars can morph into black holes through phase changes rather than pure gravitational collapse, it could explain lingering mysteries like the puzzling gap between the heaviest known neutron stars and the lightest black holes. It might also shed light on fast radio bursts, those enigmatic cosmic signals some theorists link to quark stars in transitional states. Even more radical is the idea that some black holes could revert under extreme conditions, shedding mass through quantum tunneling or Hawking radiation until they melt back into neutron star-like objects. Of course, skeptics demand more evidence. Phase transitions in neutron stars would leave subtle imprints, specific frequencies in gravitational waves, or unique neutrino emissions during supernova. Future observatories like the Einstein Telescope or space-based LISA could hunt for these fingerprints. Until then, the theory remains a dazzling possibility, a reminder that the universe's most dramatic transformations might not be violent endings but quiet shifts in nature's deepest symmetries. And if true, it means the cosmos has been hiding its fluidity in plain sight, with black holes and neutron stars as cosmic shapeshifters, bound by a hidden bond no less profound than the threads weaving space and time. What if the Big Bang wasn't a fiery explosion from a single point, but a graceful cosmic origami, a fold in the fabric of reality where time itself transforms into space? This is the heart of the no-boundary proposal, a daring vision crafted by James Hartle and Stephen Hawking that rewrites the universe's origin story. Their idea strips away the need for a singularity, that infinitely dense, law-breaking starting point, and replaces it with something far more elegant, a four-dimensional shape where beginning and boundary simply cease to exist. Imagine Earth's North Pole. Ask what lies north of it, and the question unravels, not because the planet stops, but because north loses meaning there. The no-boundary proposal suggests the universe works the same way. There's no before the Big Bang because time, as we know it, smooths into space like a river merging into the sea. To grasp this, picture the universe's birth not as a sudden eruption, but as a gentle rounding off. In classical physics, tracing cosmic expansion backward leads to a singularity, a mathematical dead end where equations explode into nonsense. But Hartle and Hawking applied quantum mechanics fuzzy logic where precise points blur into probabilities. Their model treats early cosmic time as an imaginary dimension, a mathematical trick that transforms the Big Bang's sharp point into a curved, finite surface like the rounded base of a wine glass. Here, the universe doesn't explode from nothing. It simply is with no edge, no starting gun, just a seamless transition from timeless geometry to the expanding cosmos we recognize. The brilliance of this idea lies in its symmetry. Just as a circle has no beginning or end, the no-boundary universe loops back on itself in higher dimensions, creating a self-contained whole. Hawking likened it to asking what's south of the South Pole. It's not that the answer is unknown, but that the question itself is flawed. By abolishing the singularity, the proposal sidesteps the need for divine intervention or exotic physics, offering a purely scientific account of existence that's as beautiful as it is profound. Yet the proposal isn't without controversy. Some critics argue that imaginary time, while mathematically convenient, lacks physical meaning, a sleight of hand that disguises metaphysics as physics. Others question whether the model truly avoids initial conditions or just hides them in the quantum fog. And then there's the puzzle of arrows. Our universe has a clear direction. Entropy increases, stars form, time flows forward. But a perfectly symmetrical no-boundary state would seem to lack any preferred direction, like a movie reel that plays equally well backward or forward. Hartle and Hawking countered that while the geometry is symmetric, quantum fluctuations could seed asymmetry, tipping the cosmic balance toward the expanding, entropic universe we observe. The no-boundary proposal's real test may come from cosmology's cutting edge. If the universe's early quantum state left faint imprints on the cosmic microwave background, perhaps as unexpected swirls in polarization or anomalies in large-scale structure, future telescopes like the James Webb or next-generation SIMBI observatories might detect them. Such fingerprints could reveal whether spacetime truly does smooth itself into a graceful, boundary-less beginning, or if the cosmos retains scars of a more violent birth. What makes this idea endure isn't just its mathematical elegance, but its philosophical audacity. It challenges us to rethink not just how the universe began, but what beginning even means. In a no-boundary cosmos, creation isn't an event, it's a geometry, a silent symmetry woven into the very fabric of existence. And perhaps that's the most astonishing implication of all, that the ultimate answer to where did the universe come from might be from itself, in a loop of cause and consequence so perfect it needs no outside explanation. What if our universe is just one page in an infinite cosmic library, where the laws of physics change from volume to volume like dialects of some grand universal language? This is the startling vision of string theory's landscape, a multiverse of 10 to the power of 500 possible universes, each with its own unique symmetries, constants, and even dimensions. Unlike the tidy, singular cosmos we once imagined, this landscape is a teeming jungle of mathematical possibilities, where the strength of gravity, the mass of electrons, even the number of spatial dimensions shift from universe to universe. And buried somewhere in this dizzying array is our own familiar reality, its life-friendly parameters not fine-tuned by design, but the result of cosmic randomness on an unimaginable scale. The roots of this idea stretch back to string theory's early days. To reconcile the math, theorists needed 6 extra spatial dimensions curled up so tightly they're invisible to us. But how? Calabi-Yau manifolds offered one solution, until researchers realized these shapes could fold in billions of ways, each configuration producing different physical laws. Like a cosmic kaleidoscope, a slight twist could turn a universe with strong nuclear force into one where atoms never form. Suddenly, string theory wasn't predicting a single universe but a near-infinite ensemble. Physicist Leonard Susskind dubbed this the landscape, a term evoking both richness and disquiet. After all, if every possible universe exists, does the theory lose its power to explain why ours looks the way it does? Supporters argue this isn't a bug but a feature. The landscape could solve the fine-tuning problem without invoking a designer. In a multiverse where every symmetry-breaking outcome plays out somewhere, it's no surprise we find ourselves in a rare bubble where conditions permit life, a cosmic version of the anthropic principle. Some even suggest eternal inflation, a model where space-time endlessly spawns new universes, could populate the landscape naturally. Picture a boiling pot of water, with each bubble rising to the surface representing a newborn universe with random physical constants. Our universe is just one frothy speck in an eternal simmer, yet critics blast the landscape as untestable metaphysics masquerading as science. Nobel laureate David Gross quipped it's giving up on the dream of a unique foundational theory, while Sabine Hossenfelder argues that without observable predictions, the multiverse is little better than mythology. The crux of the issue is falsifiability. If we can't interact with other universes, how do we prove they exist? Some theorists hunt for indirect evidence collisions between our universe and others that might leave bruises in the cosmic microwave background, or anomalies in particle physics that hint at hidden sector interactions. Others pin hopes on quantum gravity experiments that could reveal signatures of higher dimensions, but the boldest claims come from the intersection of cosmology and computation. If the multiverse is real, advanced civilizations might simulate universes with different symmetries, and our own reality could be one such experiment. It's a dizzying recursion, a hierarchy of simulated multiverses within multiverses, each with its own rulebook. While this veers into speculative territory, it underscores the landscape's philosophical weight. The theory doesn't just expand our notion of reality, it challenges what science can or should attempt to explain. Amid the debate, one truth remains: the landscape forces us to confront the nature of scientific progress. Is a theory valuable if it organizes possibilities, even unobservable ones, or does science demand concrete, testable predictions? Whether the multiverse is humanity's greatest leap or a dead end, its allure is undeniable. It whispers that our universe's symmetries might not be fundamental laws, but local bylaws, one set of rules in a cosmic archive we've only just begun to browse. And in that vast library, the most profound discovery might be realizing how much we've yet to read. What if the symmetries woven into the fabric of reality, the perfect mathematical constants, the clean elegance of physical laws aren't clues to a deeper truth, but lines of code in an unfathomably advanced simulation? The simulation hypothesis, once relegated to science fiction, has gained startling traction among physicists and philosophers alike, precisely because it reframes the universe's eerie order as potential evidence of design. Think of the way video game worlds operate. They rely on consistent rules to function, from gravity to light propagation. But these laws are ultimately abstractions optimized for efficiency, not fundamental truth. Could our universe's symmetries, from the precise balance of the electromagnetic force to the recursive patterns of fractal cosmology, be artifacts of similar optimization? Nick Bostrom's seminal paper lays out the trilemma at the heart of this idea. Either civilizations inevitably self-destruct before reaching post-human capabilities, they choose not to run ancestor simulations, or we're almost certainly living in one. The argument hinges on sheer probability. If advanced civilizations exist and if they have the computational power to simulate conscious minds, the number of simulated universes would dwarf the single, base reality. Statistically, the odds tilt overwhelmingly toward us being among the simulations. Symmetries like charge parity invariance or Lorentz symmetry, which keep physics consistent across scales and reference frames, could simply be error correction protocols ensuring the simulation runs smoothly. Even quantum indeterminacy might reflect computational limits, a way to reduce processing load by only rendering reality upon observation, like a video game optimizing graphics for the player's viewpoint. But critics wield Occam's razor like a scalpel. Why invoke a cosmic programmer when the universe's regularity could just as easily emerge from natural laws? The simulation hypothesis, they argue, doesn't solve mysteries, it merely pushes them up a level. If our universe is a simulation, who or what governs the rules of the simulator's reality? This leads to an infinite regress, a nesting doll paradox that offers no real explanatory power. Worse, the theory risks being unfalsifiable. If any observed anomaly can be dismissed as a glitch or intentional design choice, how could we ever disprove it? The Fermi paradox adds another wrinkle. If simulations are inevitable, where are the artifacts of their construction? Shouldn't we expect to find deliberate signatures, mathematical Easter eggs left by the programmers, or telltale pixelation at the Planck scale? Some theorists scan the cosmic microwave background for repeating patterns or anomalies that might resemble a resolution limit, while others probe high-energy particle collisions for signs of discrete spacetime. Yet decades of searching have turned up nothing conclusive. The universe's symmetries remain pristine, with no obvious fingerprints of a designer. Perhaps the most unsettling implication isn't about the universe, but us. If consciousness is substrate-independent, a pattern that could run on silicon as easily as neurons, then simulated beings would experience qualia indistinguishable from real beings. This collapses the distinction between creator and creation, raising harrowing questions about agency and purpose. Are we NPCs in someone else's experiment or participants in a cosmic art project? The simulation hypothesis doesn't just challenge our understanding of physics. It reframes existence itself as a potential performance, with symmetries as the stage directions we're only beginning to decode. Whether you find the idea thrilling or dystopian, it forces a reckoning with the limits of human knowledge. The universe's symmetries might be the closest we get to reading the source code, but for now, the compiler remains just out of reach. What if you could hold a snowflake in your hand, not just perfectly symmetrical in space, but pulsing rhythmically in time, a structure that repeats itself not through atoms, but through moments? This is the mind-bending promise of time crystals, a concept so radical it redefines what matter can be. Nobel laureate Frank Wilczek first proposed the idea in 2012, imagining a bizarre new phase of matter that breaks one of physics' most sacred symmetries, time translation invariance. Normally, the laws of physics don't care when you perform an experiment morning, midnight, a billion years from now. The outcomes should be identical. But time crystals laugh in the face of this symmetry, oscillating perpetually in their lowest energy state like a grandfather clock that ticks forever without ever being wound. The magic lies in what Wilczek called spontaneous symmetry breaking. Just as water molecules suddenly align into ice's crystalline patterns when cooled, time crystals emerge when quantum systems settle into states where time itself becomes textured. Picture a ring of atoms spaced evenly like numbers on a clock, but instead of sitting still, they flip their quantum spins in a repeating sequence 1, 2, 3, 1, 2, 3, even with zero energy input. It's as if the universe has etched a groove into time, forcing the system to rock back and forth like a needle on a cosmic record. For years, skeptics dismissed the idea as mathematical fantasy, arguing perpetual motion was impossible. But in 2017, two teams, one at Harvard, another at the University of Maryland, built the first time crystals using chains of trapped ions and nitrogen vacancy centers in diamond. These weren't tiny timekeepers in the classical sense. The crystal's periodic motion emerged from entangled quantum states, flipping spins at intervals dictated not by external forces, but by the system's own internal rhythm. Even more astonishing, these oscillations resisted perturbations, stubbornly maintaining their tempo like a metronome immune to being bumped. The implications ripple far beyond curiosity. Time crystals could revolutionize quantum computing by protecting fragile qubits from decoherence, their rhythmic stability acting as a natural error correction code. Some theorists speculate they might even model exotic physics like cosmic strings or black hole horizons, where time behaves in similarly strange ways. Yet the most profound revelation is philosophical. Time crystals prove that time, often seen as an empty stage for events, can itself become a participant folding into matter's structure. Wilczek's vision has since exploded into a thriving field, with researchers crafting time crystals from superfluid helium to superconducting qubits. Each realization forces us to rethink where order can hide, not just in the arrangement of atoms, but in the very heartbeat of reality itself. And if time can crystallize, what other symmetries might be waiting to shatter? Imagine a universe where gravity is so feeble that black holes couldn't form, where the cosmic glue holding galaxies together simply dissolves into irrelevance. The weak gravity conjecture dares to declare, nature abhors such a reality. This bold principle, emerging from the frontiers of quantum gravity, suggests there's a fundamental limit to how weak gravity can be compared to other forces, a cosmic balancing act ensuring the stability of the universe's deepest symmetries. It's as if the laws of physics have a hidden failsafe, preventing gravity from becoming too insignificant to play its part in the grand quantum symphony. At its core, the conjecture states that in any consistent theory of quantum gravity, gravity must not be the weakest force acting on a particle. There's a lower bound, a sort of gravitational floor, beneath which the delicate interplay between quantum mechanics and spacetime breaks down. Picture a tightrope walker. Gravity is the rope and the other forces are the balancing pole. If the rope becomes too slack, gravity too weak, the walker plummets into the swampland, the ominous term theorists use for seemingly plausible theories that, upon closer inspection, can't coexist with quantum gravity. The weak gravity conjecture acts like a guardrail, ensuring theories remain on the landscape of viable possibilities. This idea didn't emerge from abstract philosophizing but from concrete puzzles in string theory. When researchers tried constructing models with extremely weak gravity, they kept hitting mathematical inconsistencies, black holes that violated entropy bounds, or particles whose charges defied quantization rules. The conjecture elegantly patches these holes by asserting that electromagnetism or any other gauge force must always exert a stronger influence on a particle than gravity does. In practical terms, it means an electron's electric repulsion will forever overpower its gravitational attraction to another electron, no matter how we tweak the parameters. The implications ripple far beyond theoretical niceties. If true, the conjecture rules out certain versions of large extra dimensions popular in some string theory models, where gravity's apparent weakness in our 3D world is explained by leaking into higher dimensions. It also constrains dark energy, suggesting the cosmological constant can't be arbitrarily small without destabilizing quantum gravity's framework. Even the search for new physics feels its pull. Experiments hunting for ultra-weak forces must now contend with the possibility that nature itself has drawn a line in the sand. What's truly fascinating is how this idea intertwines with the broader swampland program, a sweeping effort to distinguish islands of consistent quantum gravity theories from the swamp of dead-end ideas. The weak gravity conjecture serves as one of its sharpest tools, a litmus test for theoretical viability. It's not just about gravity's strength, it's about preserving the universe's ability to reconcile quantum weirdness with spacetime's curvature. Break this rule and the entire edifice of quantum gravity might crumble into paradox. Critics argue the conjecture remains unproven, a useful heuristic rather than an ironclad law. Yet its predictive power is hard to ignore. From the mass of certain black holes to the behavior of extreme magnetic fields in neutron stars, observational clues are starting to align with its demands. Whether the weak gravity conjecture ultimately holds or not, it's already reshaped how we think about nature's limits, not as arbitrary lines, but as the subtle harmonies of a universe that refuses to let its symmetries unravel. And in that refusal, we might just find the keys to the quantum gravity kingdom. Deep in the cosmos, something unsettling is happening. Entire galaxy clusters are streaming toward a point beyond the edge of our observable universe, moving with inexplicable momentum as if tugged by an invisible hand. This bizarre phenomenon, known as the dark flow, defies one of cosmology's most cherished principles, isotropy, the idea that the universe looks the same in all directions. First detected in 2008 by analyzing the peculiar velocities of over 1,000 galaxy clusters, the dark flow suggests a gravitational anomaly so vast it would require mass beyond our cosmic horizon, perhaps even beyond our universe. The data came from the cosmic microwave background, the afterglow of the Big Bang. As galaxy clusters move through space, their hot gas scatters CMB photons in a way that leaves a faint imprint like footprints in cosmic snow. By mapping these distortions, astronomers found clusters hurtling at speeds up to 1,000 kilometers per second toward a patch of sky between the constellations Centaurus and Vela. The kicker: this motion can't be explained by known mass distributions. Even the Great Attractor, a colossal concentration of galaxies 500 million light-years away, lacks the gravitational muscle to account for it. The flow extends billions of light-years farther than any known structure, implying influence from something truly alien to our cosmological models. Theories attempting to explain this anomaly range from the provocative to the apocalyptic. One spine-tingling possibility: the dark flow could be evidence of a neighboring universe brushing against ours during cosmic inflation. Imagine two soap bubbles briefly touching in a froth of multiverses, their mutual gravitational pull warping space-time along the contact point. If our universe inflated alongside others in a higher dimensional bulk, as some string theory models suggest, their gravity might leak through, creating a preferential tug on matter in our observable realm. It's a cosmic version of feeling wind from a door left ajar in another room, except the door is a higher dimensional boundary, and the wind is the gravity of another reality. Less exotic but equally puzzling explanations point to primordial magnetic fields, relics from the universe's first microseconds. These fields, if strong enough, could have woven vast filaments of force stretching across the cosmos, channeling galaxy clusters like iron filings in a magnetic current. Simulations show that such fields, generated during phase transitions in the early universe, might survive to the present day, imprinting large-scale coherent motions on matter. Yet even these models struggle to explain the dark flow's sheer scale without invoking new physics. Skeptics argue the anomaly might be a systematic error, a subtle bias in how we measure cluster velocities or interpret CMB data. The Planck satellite's later analyses found weaker evidence for the flow, fueling debate. But proponents counter that Planck's methodology smoothed over small-scale anisotropies that ground-based telescopes like the Atacama Cosmology Telescope continue to probe. The truth may lie in next-generation surveys like the Euclid mission or the Simons Observatory, which will map galaxy motions with unprecedented precision. What makes the dark flow so electrifying isn't just its defiance of isotropy, but what it implies about the universe's hidden architecture. If real, it hints that our cosmic neighborhood isn't an isolated island but part of a vast, interconnected web. One where the gravitational whispers of unseen realms or primordial forces might still shape the paths of galaxies. Whether the flow ultimately proves to be a measurement glitch or a crack in cosmology's foundation, it reminds us that the universe's symmetries might be more fragile and more fascinating than we ever imagined. What if space and time aren't the unchanging stage of reality, but a shimmering mirage, a tapestry woven from threads we can't yet see? This is the radical promise of the emergent spacetime paradigm, a theory that flips conventional physics on its head by suggesting spacetime isn't fundamental at all, but an illusion conjured by something far stranger, the quantum entanglement of microscopic bits of information. Picture a three-dimensional hologram emerging from a two-dimensional surface, except the surface is an abstract web of quantum connections, and the hologram is the entire universe we perceive. At the heart of this idea is a breathtaking symmetry, not in the geometry of space, but in the hidden relationships that create it. Enter Eric Verland, a theoretical physicist who's reimagined gravity itself through this lens. His entropic gravity proposal suggests that what we experience as gravity, the force that bends starlight and anchors planets, isn't a fundamental interaction at all, but a side effect of quantum entanglement. Just as heat arises from the random motion of atoms, gravity might emerge from the way entangled quantum bits rearrange themselves to maximize entropy, a measure of disorder. Imagine shaking a box of puzzle pieces until they suddenly click into a picture. Verland argues spacetime works the same way, with gravity being the statistical tendency of quantum information to organize into what we perceive as geometry. The implications unravel like a cosmic thread. If spacetime is emergent, then black holes, those infamous destroyers of information, become labs for testing the theory. When matter falls into a black hole, its quantum information isn't lost but smeared across the event horizon like data encoded on a cosmic hard drive. This aligns eerily well with the holographic principle, where a black hole's interior is a projection of information stored on its surface. Even more striking, Verland's math reproduces Einstein's equations of general relativity without invoking spacetime's traditional curvature, as if gravity has been hiding its quantum origins in plain sight. But how do symmetries fit in? Think of a bustling city viewed from space. At ground level, streets twist and turn, but from high above, patterns emerge: radial avenues, grid layouts, symmetrical plazas. The emergent spacetime paradigm suggests nature's symmetries work the same way. Lorentz symmetry, which ensures the speed of light is constant, might not be a fundamental law but a collective effect of underlying quantum chaos. Even the smoothness of space-time could be a large-scale averaging of tiny, jittery quantum connections, like the blur of a spinning fan's blades merging into a seamless disk. Critics point to gaps in the theory, like its struggle to explain the universe's accelerating expansion without tweaking dark energy. Yet supporters counter that emergent gravity naturally accounts for dark matter's effects by modifying how mass curves spacetime at galactic scales. Some galaxies rotate too fast for their visible matter, but Verland's framework predicts these anomalies without invoking unseen particles. It's as if we've been chasing shadows while the real culprit was the stage itself, flexing under rules we're only beginning to decipher. The most profound twist: if spacetime is emergent, then the universe's deepest symmetries aren't built into its fabric. They're collective harmonies arising from countless quantum notes we've yet to hear. And that changes everything. From the birth of black holes to the fate of cosmic expansion, the emergent paradigm doesn't just rearrange the puzzle pieces, it reveals we've been missing half the box. The question now isn't just how gravity works, but what else might be hiding in the quantum code that writes reality itself. Deep in the labyrinth of abstract mathematics lies a numerical oddity so strange, it might just hold the key to the universe's deepest symmetries. Meet the octonions, an 8-dimensional number system so exotic that even mathematicians approach them with a mix of awe and caution. Unlike the familiar real numbers or even their complex cousins, octonions refuse to play by the usual rules of arithmetic. Multiply them in one order and you get a certain result, reverse the sequence and the answer changes. This bizarre property, known as non-associativity, makes them the black sheep of algebra. Yet here's the twist: these mathematical misfits might be the secret language of particle physics, encoding symmetries that govern everything from quarks to the cosmos. At the heart of their allure is a connection to the universe's fundamental forces. The standard model of particle physics is a patchwork of symmetries: SU3 for the strong nuclear force, SU2 for the weak force, U1 for electromagnetism, each governing how particles interact. For decades, physicists have hunted for a grand unified theory, GUT, that weaves these disparate forces into a single framework. Enter the octonions. Their intricate geometry mirrors the symmetry groups of particle physics so precisely, it's as if nature left a cryptic clue in higher dimensional math. The exceptional Lie group E6, a candidate for GUT symmetries, emerges naturally from octonionic algebra, hinting that the universe's forces might unify in an 8-dimensional space our senses can't perceive. What makes octonions truly special is their rarity. Of all possible number systems, only 4 are normed division algebras, mathematical structures where division makes sense and sizes can be consistently measured. The real numbers 1D, complex numbers 2D, quaternions 4D, and octonions 8D are the sole survivors, each with progressively stranger properties. Octonions sit at the edge of this hierarchy, the final puzzle piece before the math collapses into chaos. Their symmetry group, G2, is so exceptional it appears nowhere else in physics with such prominence. It's as if the universe ran out of room after 8 dimensions, packing all its mathematical magic into this one unstable, beautiful structure. But why would nature care about such esoteric math? One tantalizing clue comes from the octonions' relationship to spinors, mathematical objects that describe how particles like electrons rotate in quantum mechanics. The rotational symmetries of octonions align perfectly with the behavior of fermions, the building blocks of matter. Some theorists, like Cole-Fury, have shown that the electric charges of quarks and leptons can be derived directly from octonionic multiplication tables. Imagine the +2/3 charge of an up quark or the -1 of an electron might not be arbitrary numbers, but inevitable products of 8-dimensional arithmetic. It's a revelation that borders on alchemy, turning abstract algebra into tangible physics. The octonion dream isn't without skeptics. Critics point out that while the math is elegant, no experiment has yet confirmed its role in nature. The energy scales where octonionic symmetries might unify the forces are far beyond our particle collider's reach. Others argue the theory's beauty is its own trap, a seductive mirage that might lead physicists down a decades-long dead end, much as string theory's elegance has yet to yield testable predictions. Even advocates admit the octonion's non-associativity poses problems. If the universe's laws can't consistently agree on the order of operations, how can reality stay coherent? Yet the octonion's defenders counter with a simple question. If higher dimensions and abstract math have already explained so much, from curved spacetime to quantum entanglement, why couldn't they hold the final piece of the puzzle? The history of physics is filled with cases where useless mathematics later became the foundation of reality. Complex numbers, once dismissed as imaginary nonsense, are now essential to quantum mechanics. Perhaps octonions are the next chapter in that story, waiting for their moment to step from the shadows. Whether they ultimately crack the code of unification or remain a fascinating footnote, octonions challenge us to think bigger, to imagine a cosmos where the rules of arithmetic themselves whisper the secrets of existence. And that's the real power of this idea. It doesn't just expand our theories, it expands our sense of what's possible. After all, if an 8-dimensional number system can describe the universe's fabric, what other hidden symmetries might be waiting in the equations we've yet to write? Most theories about the universe's end paint a bleak picture, a cold, dark fade into oblivion as stars burn out and black holes evaporate. but physicist Frank Tipler offers a vision so audacious it turns cosmic doomsday into a transcendent awakening. His omega point hypothesis suggests the universe isn't stumbling toward chaos, but evolving toward a state of perfect symmetry, an endpoint where reality itself becomes infinite in intelligence, power, and complexity. It's as if the cosmos is a puzzle assembling itself piece by piece until every question finds its answer in the final, luminous click of completion. Tipler's argument hinges on a radical reimagining of cosmology's far future. While conventional models predict heat death, a lifeless expanse where entropy maxes out and all activity ceases, he sees a hidden trajectory in the math. As the universe accelerates toward its final collapse, Tipler argues, the very conditions that seem to spell doom could instead fuel an exponential rise in computational capacity. Gravitational energy from the Big Crunch, harnessed by civilizations of the distant future, might power simulations of such staggering scale that they effectively resurrect every possible consciousness that ever existed. The universe, in its final moments, wouldn't just contain intelligence, it would become intelligence, a singularity of thought so dense it borders on divinity. The symmetry here isn't spatial but informational. At the omega point, every bit of data, every quantum state, every event in cosmic history will be preserved, processed, and unified into a seamless whole. It's the ultimate holographic principle, the universe's beginning and end folding into each other like a Möbius strip, with the Big Bang's raw potential flowering into the omega point's infinite actualization. Tipler even ventures into theology, suggesting this end state aligns with concepts of God, not as a supernatural creator, but as the natural culmination of physical law. The universe, in essence, achieves self-awareness. Critics, of course, pounce on the theory's speculative leaps. The omega point relies on closed universe models where gravity eventually halts and reverses expansion, a scenario at odds with current observations of accelerating expansion driven by dark energy. Tipler counters that dark energy's properties could change over trillion-year timescales, but many cosmologists dismiss this as wishful thinking. Others question whether infinite computation is even physically possible, citing limits like Landauer's principle, which ties information processing to energy dissipation. Even if civilization could harness collapsing spacetime's energy, could it truly overcome thermodynamics' ruthless arithmetic? Yet the hypothesis fascinates because it inverts our existential anxieties. Where heat death renders life a fleeting spark in the void, the omega point frames consciousness as the universe's ultimate purpose. It's a teleology written not in scripture but in the language of general relativity and quantum information. And in that tension between cold equations and cosmic hope lies its enduring power. Whether Tipler's vision proves prophetic or poetic, it challenges us to see the universe not as a dying ember, but as a story with a last line so dazzling it bends back to illuminate the first. From the cosmic ballet of supersymmetry to the holographic whispers of an encoded universe, these 30 theories reveal just how deeply symmetry is woven into the fabric of reality, not just as a feature, but as the very scaffolding holding existence together. Whether it's string theories, vibrating filaments dancing through hidden dimensions, or the eerie precision of the anthropic principle's fine-tuning, each idea peels back another layer of the cosmic onion, offering glimpses of an order far stranger than we imagined. Some symmetries, like CPT invariants, are ironclad laws until kaons and antimatter hint at cracks in the armor. Others, like the fractal branching of the universe or the emergent geometry of spacetime, blur the line between math and metaphysics, suggesting reality might be less a fixed stage and more a living, shifting mosaic. The beauty of these theories isn't just in their elegance, it's in their audacity to question the universe's rulebook. Penrose's cyclic cosmology dares to ask if time itself can loop, while twistor theory tosses out spacetime entirely, replacing it with a symphony of higher dimensional threads. The weak gravity conjecture draws a line in the sand, declaring that even nature has limits, while the omega point rewrites apocalypse as enlightenment. And then there's the haunting question lingering behind them all. Are these symmetries the universe's way of revealing its secrets, or just the shadows of deeper truths we've yet to uncover? As we stand on the precipice of new discoveries with quantum computers probing entanglement, telescopes capturing dark flow anomalies, and colliders hunting for extra dimensions, the next breakthrough might not just confirm one of these theories but shatter our assumptions entirely. Perhaps spacetime isn't fundamental, perhaps the constants aren't constant, or perhaps, as the simulation hypothesis whispers, we're mistaking the code for the cosmos. So here's the real challenge. Don't just marvel at these ideas, wrestle with them. Which vision of symmetry feels like a key to reality's lock? Is the universe a hologram, a fractal, or a cosmic neural network? A multiverse or a mirage? The answer isn't just out there, it's in how we choose to look. Drop your thoughts below. Let's see which theory sparks your cosmic curiosity.